All right. So, what do logarithms have to do with elections? Well, if you go look at the logarithms of the yes to no ratios of Republicans and Democrats on ranked choice voting, you'll see that they move in perfect parallel. So they have a lot to do with it, but you have to understand why. Okay. So what we're going to do is a little thought experiment. It's actually easier to start this with complex numbers than it is with real numbers. So what we're going to do is a change of reference frame. Okay. We're going to make 3 circles here. So this interior one is the unit circle of length 1. Okay. There's no such thing as 0. There's only the observer who's at the center of the reference frame. So take the word 0 and every time you see it and replace it with the word observer, because that's literally what it is. So we have a vector, let's say that's at 45 degrees at 2 units. Okay. And we have another vector that's 3 units of length, that's at 60 degrees over here. So this is B, and this is A. What does it mean to divide B by A? Okay, so this is vector B, and this is vector A. The expression B over A, whether B is a complex number, a real number, or A is a complex number or a real number, it means to measure B in terms of A as if A were 1 unit of length in the forward direction. That's what it means. So since this has a length of 2 and this has a length of 3, this equals vector C. C has a magnitude of 1.5, 3 over 2, and it has a facing of 15 degrees because there's a 15-degree difference from A to B. So that plots vector C at 1.5 units at 15 degrees. So here's C. And this, we're going to call this A prime, which is equal to 1. A prime is A over A, which is 1 plus 0i. So to divide by A means to take the entire reference frame and any other vectors that are in it, D, E, F, and it means to view those vectors from the perspective of an observer facing in the direction of A, who perceives that as his forward direction, and the magnitude of, from him to A as a unit of length. That's what division is. It is a change of reference frame. Now, if these were only real numbers, it would still be the exact same thing. A is 2. I'm going to draw them just a little parallel to each other so it's not confusing. B is 3. A divided by B, well, since the relative facing of both vectors is the same, then B divided by A is also a real number because there's no change in facing. Because now when I divide A by itself to get to 1, and B divided by A to get to 1.5, I have 2 forward vectors, then their only difference is their change in magnitude. Okay, well, now that we've done all that, we're only dealing with real numbers for now. What does it mean if I say I'm going to write the word A double prime? A double prime equals 27 votes for Trump. B double prime equals 3 votes for Kamala. I'm going to do this in base 3 instead of base E for a moment. So that's equal to E to the A prime. And this is equal to B. So I'm going to put 3. 3 to the A prime. And this is equal to 3 to the B prime. Well, A prime is equal to 3 because 3 to the third power is 27. B prime is 1 because 3 to the first power is 3. C, we're going to define U as 1/2 A plus B prime, which is equal to 2. Define V as 1/2 A prime minus B prime, which is equal to 1. 3 minus 1 is 2, times 1/2 is 1. What this means then is that A double prime plus B double prime is equal to 3 to the U, which is 3 squared, times 3 to the positive V plus 3 to the negative V, which is equal to 9 times 3 plus 1/3. So this term, e to the u, 3e to the u, is what we call relative unity. The logarithmic mean of a and b is relative unity. Okay? So you have an observer. Here's 1 unit. Here's 3. Here's 27. Okay? I'm going to put this in red, green, and blue. Then we have their relative unity, which is 9. This is 9. 3. Relative unity is the logarithmic mean. And what we're going to do is transform this reference frame, since they're all in the same direction, we don't have to rotate anything, such that 9 is now the unit of length. Well, when you do that, 9 becomes 1. 9 divided by 9 is 1. 3 becomes 1/3, because 3 divided by 9 is 1/3. And 27 in blue becomes 3, because 27 divided by 9 is 3. So here there was no change of rotation because everything was real numbers, but there was still a change of magnitude. That's a hyperbolic rotation. So whenever you see e to the something, where something is some complex number a, okay, it means that the logarithmic mean, let's say e to the b minus e to the negative b, these are all complex numbers now, okay? This is the logarithmic mean of the two vectors, and this is the logarithmic midpoint of the logarithmic difference. So the mean vector sum and the mean vector difference is what's really happening here. Now, if you were to take this example real quick and extend it to the complex numbers, you would see that this is actually very much true. Okay? So once again, we have our 3 unit circles. And what we're going to do is put 2 vectors. I'm going to keep the math really easy here, just by choosing easy numbers. Something of length 3 at 135 degrees, and something at length 2 at 45 degrees. Well, the logarithmic mean is I don't know what the exact thing is, but it's supposed to be something like 2.2 or something. And then, but the angle, though, will still be 90 degrees. And what this does is it creates an arc of an equiangular spiral, or a logarithmic spiral, where green is the relative unity of that spiral. So now if we divide by green, well, what we end up with is, I'm going to put these in red real quick. And that's blue. Well, once we divide red, green, and blue by green, green goes here. Red goes here-ish. And blue goes here. And we still have a logarithmic spiral passing through red, green, and blue. Okay? There's a lot of nuance to this stuff. But this green vector is e to the u, relative unity. And then red and blue is e to the v and e to the negative v. All right, so now we're going to use e now, base e. And, okay, so we have this expression. Trump is 27 votes. Kamala's 3 votes. So what then we have here is the identity. Okay? If we divide this by 3 to the u, which is 9, okay, then what we're saying is that a, not a double prime or a prime, a equals 3 and b equals 1/3. So Trump has 3 votes and Kamala has 1/3 of a vote. Okay? So if a is 3 to the v and b is 3 to the negative v, then a is equal to we're going to put this in its logarithmic notation. So let's just start the example over from here. All right, so we have a. These are the original vote totals we're given. That's equal to a double prime. That's Trump. These would be the original precinct integers. 3 is b, double prime. Okay. From this, we get a prime equals the ln of 27. I don't care what that is. You can calculate it yourself. I'm not writing it out. B prime is the ln of 3. U equals 1/2 the ln of 27. I'm just going to write a prime, b prime. A prime plus b prime. V equals 1/2 a prime minus b prime. Which means that a is equal to e to the positive v, which is cosh v plus sinc v. B is e to the negative v, which is, after simplification, cosh positive v minus sinc positive v. C is equal to e to the u, And that's whatever this is. So then we have A plus B in their original double prime forms, the original integers, is equal to C, A plus B, 3 plus 1/3. Nine times 3 plus 1/3. Okay, well, from this, can we figure out what A plus B is? Well, of course. I'm going to add cosh V plus sinc V to cosh V minus sinc V. And guess what? I get 2 cosh V. So, we have A plus B is therefore equal to 2 cosh V. All right, so then what's the percentage A over A plus B? Because whether you write it as trump 27, 27 plus 3, it's also equal to 3 over 3 plus 1/3. Is it not? Remember, to divide by something means to measure something in terms of another. So we're saying that we're measuring A plus A in terms of A plus B combined. Well, thankfully, we know what that is. It's 2 cosh V. Makes our lives really easy. Okay? So then A over A plus B is cosh plus sinc of VV over 2 cosh V. B is cosh minus over 2 cosh V. So guess what happens when you add them together? You get A plus B over A plus B. Well, cosh plus sinc minus sinc gives you 2 cosh. So you get 2 cosh over 2 cosh. So you get 1. That's why percentages add up to 100%. So now that you know what a percentage is, and you know that it's fundamentally a hyperbolic entity, this is why percentages, a linear change in percentage, is not a linear change in ratio. Think of it this way, taking this graph in front of us. If you go from 50% to 55%, the ratio went from 1 to 1 to something that is almost equal to 1 to 1. It's just slightly favored, right? But if you went from 90% to 95%, you just went from a 9 to 1 ratio to nearly an 18 to 1 ratio. You just double your ratio by going from 90 to 95, approximately. If you went from 95% to 100, you just went from a 18 to 1 ratio to an infinity to 1 ratio. So a linear change in percentage is not a linear change in ratio, is it? Because it's fundamentally a hyperbolic entity in the form of cosh plus sinc over 2 cosh. That's why. Now, as B goes to 0 relative to A, you get 100% of the vote because cosh and sinc are also nearly equal to each other as V goes to infinity. So as the ratio goes to infinity, cosh v equals sinc v. So then you get 2 cosh over 2 cosh, which is 100%. You see how this is all making sense now? Logarithms, however, we don't have that problem with logarithms. So the reason these graphs look kind of similar, the percentages and the logarithms of the vote ratios, is because the percentages are they aren't near the extremes, right? So in this graph, the percentages are going from 70 to 30. They're sort of in that same range. And in this range, a change in percentage is somewhat linear in terms of ratios and logarithms. It could be approximated linearly. But when things start getting up in the stratosphere, you have to use logarithms. It becomes too extreme. So notice that the graph of the percentages, because they're in this Goldilocks zone where they could be approximated by linear changes in ratios and logarithms, that it looks very similar to the logarithmic graph. So what do logarithms do? Well, logarithms make linear changes in scale. And what is voting about? It's not about how many votes you got. It's about how many more votes you got than the other guy. The scale of votes. I need to have a 1-to-1 ratio of votes plus 1 to beat you. If I get 5 million votes, I still lose if you got 5 million and 1. It's not how many votes. It's the ratio of votes. And what makes changes in ratio linear? Logarithms. And thus, logarithms are the way in which we examine elections. So all of these manifolds equations that you see for the presidential, the Senate race, and all these other races I wrote about in the long version of the paper, when I give you the percentage forms, GH and alpha, I'm doing that for the normies. I'm doing that because you're usually in front of a mathematically illiterate court. Members of the public and of the judicial system aren't math experts. If you really wanted to dig as hard as you could into these manifolds that are rigging the elections in 2 or 4 races at once with the complex numbers and the quaternions, you got to use logarithms. You have logarithmic manifolds. Thankfully, so long as the percentages involved of these manifolds are not in the extremes up here, we can well approximate the rig just using percentages instead of the logarithms, and we can litigate that instead. Except in this case, we actually have to use logarithms. So I just want you to understand the difference between a logarithm and a percentage. A percentage is fundamentally a hyperbolic function in the form of cosh plus sinc over 2 cosh. Whereas a logarithm is just cosh plus sinc. It's e to the u, right? It's just cosh plus sinc. You'll be like, whoa, that makes it hyperbolic. Maybe. Maybe not, depending on how you want to interpret that. But at the end of the day, a logarithm is just cosh plus sinc, and a percentage is the same thing. It's the logarithm, but now divided by 2 cosh. So you get some really strong nonlinear behavior in percentages when things start to get near 100%. To give you an example of that, suppose the mean of standard deviation of somebody's percentage was 50%, right? The mean, and they had a 10% standard deviation. Okay, well, in this range, percentages behave in a linear manner. So there really wouldn't be much of an issue there. You'd probably get a fairly normal looking distribution. But what if I now said, actually, their mean was 85, and their standard deviation was 10%. Well, that doesn't make sense because now you're going to have more than 100% of the vote in some precincts. So that can't be true. So what ends up happening is if you do it in percentages, you get a very strong left or right tail distribution. You'll get a mean value of 85, and then half of the data points will be clustered under this green line, but the other half will be way, way down here. There's a huge difference from here to here. But if you were to look at it in terms of logarithms, you would actually see that the logarithm from brown to yellow, the difference is the same as the logarithm from brown to green, even though in terms of percentages, it looks massive. When you look at elections, prior to 2020 at least, although percentages themselves, or logarithms of the ratios themselves, are not normally distributed, you'll notice that things like the difference in the logarithms of the early percentage, A over B, minus the mail-in percentage, C over D, you'll notice that those are normally distributed across the precincts. But if you did it in terms of percentages themselves, you would still get a non-normal distribution. So that's why we use logarithms, okay? Now, what about r squared? Now, what is an r squared measure, which is a correlation coefficient? So, when you take the regression, y equals some function of x as your regression, the r squared of that is 1 minus RSS over TSS. And the residual sum of squares is how much your function missed by against the actual data. The total sum of squares is how much the baseline average as a model misses. Okay. So, but what this, if you really look at this, it says r squared equals TSS minus RSS over TSS. Oh, that's interesting. So it's saying the difference from the total sum of squares to the residual sum of squares, which tells you absolutely nothing about the difference in scale between them, divided by the total sum of squares to then at least make that scale somewhat meaningful. But what's the problem with an r squared value? Well, if your function that you're using the regression in, if it has a constant, just some null constant plus, something like this, it can never be less than 0, because by including a constant, you have included the baseline average. So any model you build with a constant will always be the same or better than the baseline average. And thus r squared can never be less than 0 unless you remove a constant from your model. But even if you do remove the constant so that r squared can go all the way to negative infinity, it's still capped at 1. So it can go from negative infinity to 1. Well, that's kind of weird. And if we were to really dig into this, it's really hard. We would see that it's ultimately in the form of hyperbolic cosecants and secants, which I don't want to get into. This derivation took long enough to teach you what a percentage is. Okay. Is there something better that we can do? Oh, the reason this matters is because when we simulate these rigged elections, we're going to have to get r squared values. And if our r squared value was close to 0 or close to 1, we start hitting limits that we can't go beyond. So what we're going to do instead is, instead of using r squared, which is RSS over TSS, okay, we're going to use another metric called psi, which is equal to the ln of the residual sum of squareds over the total sum of squareds. So let's say that RSS over TSS was equal to 4. 1/4, my bad. Well, this would mean that this is a very good model because it's 4 times better at predicting y than just taking the baseline average of TSS. Which means that an r squared equals 1 is synonymous with psi equals negative infinity. Because as your residual sum of squares goes to 0 in respect to the total sum of squares, then you have no error. Well, then the ln of 0 is negative infinity, so psi equals negative infinity. Okay. As your r squared goes to some abysmal value, well, this would mean that RSS equals TSS. So then psi would also equal 0. Well, wow, this is starting to make sense now. When r squared is 0, psi is 0. Because the ln of, if the RSS equals a TSS, which is equal to 1, well, the ln of that is 0. And if r squared is really bad, you took the constant out of your model and we're going to put negative infinity, well, then psi will also be positive infinity. So that would be the baseline model of just picking a random real number amongst the continuum of real numbers from 0 to Graham's number. Okay? That's what r squared negative infinity would be. But it also translates to r squared psi equals positive infinity. So psi, r squared 1 is psi negative infinity, r squared 0 is psi 0, r squared negative infinity is psi equals positive infinity. Now, there's a little limit involving logarithms in general. And you get the limit of the ln of x plus 1 plus x over x, as x goes to 0, is equal to x. Okay? Is equal to 1. Now, we never actually use positive and negative infinity. We just say very large or very small. So what does that mean? And this is actually fundamental for other things too, this identity. It just says that ln of 1 plus x equals x for very small x. Why does this matter? Because it says that when our r squared values get really, really close, or our psi's get really close to 0, it means we're taking the ln of things that are in the form of very small x. Okay? So RSS over TSS equals 1 plus a very small number. Well, then that is just equal to whatever the hell the number was. If it was positive, it was positive. If it was negative, it was negative. So when that happens, the r squared values are no longer normally distributed in respect to the logarithms, in respect to psi. But now that RSS is some sum of squares and TSS is some sum of squares, we actually have to take the square root of psi to get a normal distribution. But this only happens when you get near the extremes. when the r squared is approaching 0. Okay. Now, r squareds can only be positive numbers in general, but they could be negative if you take the constant out. The thing that we're going to have, though, is that since the RSS over TSS will always be a positive number, right? When you take the distribution, okay, of the psi values after our simulations, you're not going to get a normal distribution. Well, this is after you take the square root, because they're going to be close to 0 to begin with. You're going to get what's called a half-folded distribution, where you only see one half of a bell curve. And we use the Darling test, and there's a few others just to confirm that it's a perfect half-fold. So after we do, 1,000, 10,000 simulations of an election, we're going to take whatever our psi values are, okay, and we're just going to produce their negatives. We're going to produce a negative list. And then we're going to run our test for mean to make sure that it's a normally distributed set, which you'll see here that I wrote. Shapiro-Walk and the Anderson-Darling test, okay? Once we know that the compilation of the simulation results in terms of psi with its negative counterparts are a normally distributed, we can then project through mean and standard deviation what the sigma value of an election is, whether it is a probability of this actually happening in the real election that was given to us in the cast vote record. So that ends this lecture, and see you in the next video.